All right, so our next topic starts off as an old classical problem. So given any planar map, we can color with 4 colors so that neighboring regions get distinct colors. So the idea here is that you're drawing a map of counties or countries, and the idea is that you should be able to color those counties or countries with at most 4 colors, possibly fewer. Now, one of the restrictions is that when we talk about counties or countries, they have to have only one connected region in the plane. So we aren't talking about things like islands. This theorem, by the way, was only finally proven in the 1970s using a computer-aided proof. However, I need to state what the relationship with graph theory is. So the idea is, suppose you have some sort of map with regions like so. Decide to add a vertex for every capital city in each region, and then put an edge between 2 capitals if those corresponding regions share a boundary. As so. And notice the rule about sharing a boundary. It's a technical definition. We're talking about an actual segment that's one-dimensional and not just a corner. So for instance, when you're dealing with the 4 corners states, the corresponding graph is a square, not a complete graph. Or once you've created this, you see that you end up with a graph. And the point is that we choose to color the regions, the capitals, with the color of the region. And so the point is, if there's an edge between 2 vertices, they have to get distinct colors. Like so. And so here I'm just coloring the outside with alternating colors red and blue. And then I get to this last vertex, and I see I cannot color it red or blue because it's adjacent to a red or blue vertex. So we see that we need a 3rd color. And then the vertex in the middle is surrounded by 3 distinct colors, so it needs a 4th color. This is an example of a region where we need exactly 4 colors. In this case, we can prove that you can't do it in less, because the outside 5 cycle, if you could 2-color it, then it would be a bipartite graph. In general, a graph can be assigned 2 colors if and only if it's bipartite. So we see we need at least 3 colors, and the vertex in the middle is adjacent to all the others, so we see it needs to get a distinct color on its own. So this is an example of what's called a planar graph that uses 4 colors. So now we can get into the more general theory. Given a set of colors, which we call C, a function from the vertices of graph to C is a coloring if for every edge in the graph, the endpoints of the edge get distinct colors. So some real-world applications would be class scheduling. Your vertices represent classes and edges represent classes that can't meet at the same time, and a coloring would be an actual schedule. Similarly, you could schedule meetings between different committees where you have an edge between 2 committees if they have a member in common. So then a coloring would correspond to a way to actually assign all the possible meetings so that every committee meets. And so then we let chi of G be the minimum number of colors in any coloring of a graph G. So let's look at some minor results about chromatic numbers. So chi of G of a graph is 1 if and only if G is edgeless. If G has no edges at all, you can color every vertex the same color without a problem. Next, chi of G is 2 if and only if the graph is bipartite. Because remember, in a bipartite graph, you can separate the vertices into 2 groups so that the edges have to have one endpoint in each group. In particular, every edge gets the endpoints get distinct colors. On the other hand, the second you have an odd cycle, it can't be bipartite. And then you can see it can't be 2-colored because as you alternate the colors going around the cycle, you eventually reach a vertex that's adjacent to 2 vertices of different colors. Finally, if you have a vertex such that his neighborhood is all the other vertices, then you can see that chi of G is equal to chi of G minus V plus 1. In other words, that vertex V has to get a distinct color from the rest of the graph. On top of that, that means implying induction, chi of g is equal to the number of vertices of your graph if and only if you have a complete graph. As soon as you have a missing edge, then you can try to color those vertices the same color. In fact, leading off of the bipartite case in this complete graph case, the chromatic number of a complete k-partite graph is exactly k. You assign each vertex in the same part to have the exact same color, so you end up using k colors, and then you see that the edges have to go between different parts, so the endpoints have distinct colors. All right, now we're going to prove some bounds for the chromatic number. First, the chromatic number is bounded from below by the clique number, and bounded from above by the maximum degree of the graph plus 1. So we're going to prove this lower bound first. And so let K be any clique of the graph G, and we're going to let F be any coloring. Then by definition of coloring, F of U has to be not equal to F of V for any U and V and K. In particular, that means that if we look at the set of colors used on vertices in K, the number of such colors is equal to the size of K, because each vertex in K got a distinct color. Notice that this is a subset of the total set of colors, so we have to have an inequality here. And thus now if we focus on the case where K is a maximum clique, then the size of capital K is the clique number. Meanwhile, on the other hand, this is just A coloring, so this tells us that this must be true for any set of colors where there's a proper coloring. Particularly if we take a minimum coloring, the same property has to be satisfied. So the minimum number of colors in a coloring has to be at least the size of the clique, largest clique. And now we can prove the upper bound as well. We want to prove that chi of g is at most capital delta G plus 1. We're going to prove that by induction on the size of the graph. So suppose you found a vertex of maximum degree. Delete that vertex. By induction, you know that the remaining graph can be colored in delta G minus V plus 1 many colors. Deleting a vertex can only decrease the maximum degree, so we do have a coloring of G minus V using our given number of colors. So take such a coloring. Now let's look at what the coloring does to the neighbors of V. So in the worst case scenario, every neighbor of V has a distinct color. So the number of colors used is at most the size of the neighborhood. By construction, that's actually the maximum degree. And since we have maximum degree plus 1 many colors to work from, this tells us there must be a color that's not in this set. So we set f of v to that color. This also gives you an algorithm for coloring such a graph. You just take a maximum degree vertex and choose to color it last, and then recursively color the rest of the graph first. All right, so now we're going to give some other bounds for the chromatic number of a graph. 2 of these are related to homework problems, but the other one will do. So another upper bound is that chi of g is bounded from above by 1 plus this expression. This is the maximum minimum degree over all induced subgraphs. We also get another lower bound that chi of g is at least the number of vertices of the graph divided by the largest independent set. Finally, the last bound will actually proves that chi of g is bounded from above by this expression. So it's 1/2 plus the square root of twice the number of edges plus 1/4. This last one is more of an arithmetic proof. So let's see why it's true. Suppose that the chromatic number of a graph is k, which means there has to be a proper coloring from the vertices to the integers 1 through k. For any 2 distinct colors, look at the vertices that got those 2 colors. The claim is that that cannot be an independent set. If it were, then gluing those 2 color classes together would give you a smaller coloring. In other words, recolor all the vertices you colored J with the color I instead. And now you have a coloring that uses K minus 1 colors, which contradicts the fact that the chromatic number is k. So the fact that this is not independent is important. Note that the individual pre-images are independent sets, and so as a result, for every distinct pair of colors, we know there has to be an edge in the graph where one endpoint was colored I and the other endpoint was colored J. In other words, we already can see that this is a bipartite graph, and we're claiming it's not edgeless, so it has to have at least one edge. Well then, that means that the number of edges in G has a lower bound, namely, for any pair of distinct colors, we have at least one edge. So the number of edges is at least the number of ways to pick a pair of distinct colors, and there's k choose too many ways to do that, also known as k times k minus 1 divided by 2. And then the rest of the proof is just algebra. Namely, you multiply both sides by 2 and distribute the k. Then we complete the square on the left-hand side. The missing term is 1/4, so we add it to both sides. And then the last step is to just take the square root of both sides and then add 1/2.